So, good evening. First of all, can I thank you for inviting me here today. This is indeed my first visit to Dubai. I've been here 36 hours almost, so I'm having a really great time. And it's a great honour to be invited to give this Sir Maurice Flanagan lecture. Yes, it's quite a long title. It could have been longer. I will try not to talk for too long. You'll find I get very enthusiastic about the subjects I'm going to be talking about. I very much like to be in what I call BBC mode. So the BBC aims to inform, educate and entertain, and hopefully I'm going to manage all three of those this evening. That's the aim anyhow. I'm going to be giving a short overview of what the Royal Aeronautical Society does for some of those of you who are visitors. I have the honour of being the president this year, so I am literally halfway through. So I've done 6 months, I have 6 months to go. So being able to visit some of the more, should I say from the UK viewpoint, exotic locations of the Royal Aero Society is absolutely fantastic. So it's really great to be here. I'm going to talk a little bit about why we need environmentally friendly aircraft design, and then talk about high aspect ratio wings. That means longer wings. I am sure you are going to start seeing longer wings on aircraft within the next 5-10 years. And then I'll talk about some research at Bristol on doing tests on them, and also talking about folding wingtips. So this is one of the enabling technologies, and then we'll draw some short conclusions. Some of the videos I'm going to show, I put a little health warning on, are not meant to put you off flying, but they are supposed to tell you some of the things that can go wrong unless the engineers get their sums and their designs correctly. So the Royal Aero Society has been going for over 150 years. It was founded by 6 Victorian gentlemen for the advancement of aerial navigation and observations in aerology. And you remember in 1866, that's before the Wright brothers were born, we had balloons. But these founders were real visionaries of seeing how the aeronautical sciences would develop. The Aero Society has around 25,000 members all around the world, so over 100 countries, and we have a network of 70 branches and divisions. And we run about 400 conferences, workshops and events each year. So our vision is to be recognised as the leading professional community and independent source of knowledge in aerospace, aviation and space. So that's one of the important things that distinguishes us from other professional societies, in that only about 50% of us are engineers. The rest of us are pilots or work in the Air Force or are lawyers or medics, but the many, many facets that go up to make this wonderful aviation and aerospace community that we have. And space itself is becoming more important. I don't know if some of you have noticed I have this medal around my neck. This is the President's Travelling Medal. There's a copy in Hamilton Place that comes out once a year when a new president is announced. This medal has been to the International Space Station and back. So Tim Peake, one of the UK's only astronauts who's a fellow of the Society, took the medal there. So I'm this travels around the country or around the world with me at the minute. So again, we're aiming to provide influence and leadership. We aim to attract and support a diverse and active membership, both nationally and internationally. And so things like this meeting here and your local branch here in the Emirates are really important for all levels of people involved in the aerospace community. We're also a guardian of professional standards, so people who want to become chartered engineers in the UK, we are part of that organisation that helps to certify people for having a range of competence, and also for the universities, so to accredit them. And we're also a charity as well, which has some aspects. So what are the sort of things that we do? Well, we have these branches and divisions around the world. So you have events like the one today where a speaker will come and hopefully inspire you and entertain you for the next 45 minutes. That's my aim for this evening. We also have a number of specialist committees, so on things like avionics, flight simulation, human-powered flight. So these specialist committees will organise conferences, they will organise documents. So the Greener by Design group, for instance, has written several documents which have then gone on to the government to advise on environmental effects. And you don't have to be, important thing is we're international, and you can sort of join in with the activities of these groups even if you're not based in the UK. We also have a number of publications. So Aerospace is a monthly edition which all members get. So there's also the Aeronautical Journal. Part of our remit is to be a learned society. So that is where researchers, such as those in universities and sometimes from industry, will write learned articles. Perhaps a highlight of Aerospace is every month the president has to write a page worth of what he did. And I'm sure my visit for Dubai will appear in the January edition. We also have corporate members, so we're very happy to have and very appreciative of the efforts that Emirates, for instance, does in helping with the society. But it's a two-way interaction. So some of the things we do, say with careers or helping the younger members, can also then help the corporate members. But again, we've got over 200 of those, and again from all over the world, so various universities or other large names in industry. We run an event called Cool Aeronautics. So one of the important things we need to do is to inspire the younger generations. So we try to get out and attract the 10 and 11-year-olds to tell them what an exciting careers there are to be had in aerospace, and particularly to ensure the teachers understand that. One of the problems we have in the UK and it's in other countries is trying to get more young girls to actually say, right, engineering is a career that I can actually go and do. And also we just finished something called Schools Build a Plane, where I think we had 4 or 5 planes. This was a project sponsored by Boeing, where various schools and colleges in the UK over a period of 2 to 3 years actually built an aircraft. Some of them got flown at the Farnborough Air Show, and they've all been sold on to customers. So they were all certified, and it's a fantastic experience for not just the school building it, but other local schools and colleges to see what actually, hands-on engineering actually meant. And another sort of activity is the rocketry challenge. So again, we're aiming at, very young people all the way through to people who have work in industry and then those who have retired. Anyhow, that's my selling point for about the Aeronautical Society. Let's talk a little bit about environmental aspects of aircraft design. So this is some figures here showing the average fuel burn starting at 1960. So the Boeing 707 is quite often taken as the reference point. So this is taking us along to about 2012, 2013. The blue line is the one we'll look at. So this is looking at the fuel per passenger kilometre. And you can see that we've got about a 45% reduction in that time span, putting an average on there, sort of just over 1% a year. So I don't know about this part of the world, but in the UK, the environmentalists are really putting a lot of pressure on aerospace and saying that aerospace is a big problem. But if you look at how much aircraft have improved, you could say we've been doing a really good job. Where the problem comes, though, is if we look at the CO2 emissions, and we'll see that this graph, so we're on track again to triple. So that's shouldn't be a 45% reduction. That's a 45% increase. So why is CO2 increasing whereas the actual performance is going down? And this is a graph recently produced from Airbus. And what that is telling us is this is our growth forecast. So we are predicted to have over 4% growth per annum in the number of aircraft over the next 10, 20, 30 years. So although aircraft are becoming much more efficient, they're also, the number of them is increasing as well. And again, where are these aircraft coming? Well, a lot of new deliveries, some 14,000 or so are going to retire, but we're still talking a number of 39,000 is the prediction from Airbus. Boeing have similar numbers. And if we look at where those aircraft are likely to appear, Asia and the Pacific is predicted to be a really big growth area. So there's some parts of the world, unlike America or Europe, where there is lots more capacity for people wanting to use aircraft. So we're in the environment of, okay, we're improving aircraft performance, we're reducing its environmental effect, but also then we're still trying to, because of the large number of predictions of predicted air travel increase, we need to reduce that further. So the European Union has what's called a Flight Path 2050 initiative, and that's got targets compared to the year 2000. And this isn't just per aircraft, this is in total. So it's aiming at a 75% reduction in CO2, emission-free taxiing, big reductions in NOx and noise. I don't know if that's a typical Boeing 707, but it certainly doesn't look particularly environmentally friendly, does it? So there's a big initiative to try to reduce the effect of aircraft. Whether that is going to be fast enough in terms of global warming or what some people are asking for, we will have to see. But one of the things that we need to do is to produce more environmentally friendly aircraft, and also we need to have much faster ways of designing and certifying. Typically it takes 8-9 years from the first idea to actually getting an aircraft to fly. We need to reduce that much quicker, and we need to do that in many ways. I'm going to be talking about the airframe itself, so I'm not going to talk about noise, I'm not going to talk about propulsion. But if we look at aircraft design, so this is a plot showing speed, and that's again against altitude, and all aircraft have a particular sweet spot that they are designed for. So say mid-Atlantic, mid-cruise, and what the engineers aim for is the best aerodynamic shape and also the minimum weight that can be achieved at. But the aircraft is only designed at a single point. So all these other test points, which are the black dots, the aircraft is not going to perform quite as well. Now, I apologize. So Stephen Hawking, who wrote the book about black holes, he said for every equation that you put in, you are going to lose half your audience. So I've got 2 equations tonight, so I'm afraid that the 3/4 of you will have to leave now. But no, right, do not worry about the equation. This is something the first year engineers learn about. It's called the Breguet range equation. And what that tells you is that this range is a function of speed, of the engine, aerodynamics, and the weight. And notwithstanding the mathematics, what it tells you from a physics viewpoint is that you can either improve your range or reduce the fuel burn if you have better aerodynamics, less weight, or better engines. And it doesn't matter what technology, whether you're using composites or clever aerodynamic devices, like the NEOs, all you've got in terms of physics is those 3 ways of improving performance. So how are we going to do that? So there's a whole list of topics. So we can use carbon fiber composites. So that's been used a lot. So things like the A350 and the Dreamliner are now 50% composite, primarily to reduce the weight. We've got the NEOs, which improve engine efficiency, things like biofuels. There's a lot of work being looked at using all electric aircraft, but that isn't going to work on small, family-sized cars like an Uber taxi that flies, yes, but you cannot get a battery that's going to fly a 747 from Europe to America for many, many years to come. Improved air traffic control is another good way of using the fuel. And there's lots of sort of clever aerodynamic things that we can do as well. The one I'm going to worry about tonight or tell you about is increasing the aspect ratio, so making the wings long. So rather than sitting around waiting for better batteries, as engineers we've got to find ways that can reduce the fuel burn, reduce the energy requirement. And even if we have everything driven by batteries, we still want to reduce the amount of electricity that is generated. We could go to some more fancier aircraft designs. So things like a blended wing body 10 years ago were seen to be the most obvious design. That's not quite flavour of the month now. That's a design where 15% or so of the lift comes in the fuselage. Forward swept wings, theoretically gives you better aerodynamics, but the longer wings seem to be the current flavour for that. Now, when we're doing a design, we've not only got to make sure that we are efficient, but we need to make sure that our aircraft is strong enough to withstand the loads that we are coping with in flight. So these are not made up. In theory, that tail got stuck on and the aircraft flew again. If you look on the left-hand side here from this impact, and hey, we've lost the end of the wingtip. So you've got to design a structure that is strong enough, but you also, we saw there in that previous slide how we want to make the aircraft as light as possible. So the aerospace engineer is always trying to trade off this compromise between strength and weight. One of the things we're going to be talking about, and hopefully one of the things you're going to learn, is what is aeroelasticity. So I hold what's called the Sir George White Chair of Aerospace at Bristol. The first holder was something called Roderick Collar, and he invented this triangle that says we have the interaction between elastic forces, dynamic forces, and inertial forces. And this affects the entire performance of the aircraft, how it deflects in flight. There's some things that can happen which are not so good. So this is something called flutter. And what we've got here is a model wing about 1 meter long hanging out the bottom of an F-15. And what is happening, this is in real time, this time trace is showing the response. There's no excitation, just the turbulence. The plane is slowly reducing in altitude. And my question for you is, would you stop the plane in time? And
terminate. Knock it off. We lost it.
Right. So that's called flutter. That's a violent, unstable oscillation, which, as you see, can result in violent structural failure. We don't want that to happen. Aero engineers know about that. But you need to design your aircraft wing so it's strong enough so that doesn't occur. Some years ago, I was flying back from America to Europe, and people who know me know that I use the plane journey to prepare the next day's presentation. I would argue that it's fresh in my mind. And we sat down in the plane. I was talking about flutter, and the family sat next to me said, "Oh, that's very exciting. You're doing a presentation about aeroplanes, and oh, you have some videos. Please can we look at your videos?" And I'm going, "No." And eventually, after about 5 minutes of them prodding me, I said, "Okay, but there's a health warning on this. You do not want to watch this video." So they watched it, and yes, they went a bit white, and they said, "No, we did not want to watch that video, and please can you promise that for the next 7 hours that is not going to happen." So modern aircraft, the more flexible they get, the more you've got to ensure that some of these dynamic behavior don't occur. We've also got to ensure that we're strong enough to deal with our loads. So again, you sit there in the plane and the pilot says, "Right, please buckle up, we're going through turbulence." So you've got to make sure your aircraft is strong enough to deal with that. We've got to deal with landing, maneuvers on the ground. with the maneuvers in flight. So again, it's things where if we get larger loads, we get more stress, so therefore we need a bigger structure to reduce that stress, and therefore that gives us more weight. So we're always got this, again, trade-off between weight and performance. This is a video taken on a 787 going through bumpy air, and you can see the wingtip will start to bounce around, but that control surface is the typical way of controlling that at the minute. You'll see that the wingtip bounces along a lot faster than that. That's the one where the passengers are actually going to feel what is known as a rigid body motion. Now the trouble with that, it works, but it means you've got to have an active control system and a lot of sensing and actuation. Why can't you do something that is passive, so will automatically alleviate the loads? Okay, so we've seen Breguet, that's Breguet again. How can we use that, or how can we use flexibility to change that so we can make the shape bend in a way to give us improved aerodynamics? We can reduce the weight by increasing the speed that flutter occurs. We can reduce the weight through loads alleviation. We can use non-linear devices, I'll talk about. We can improve the engine blades. And we can also, what you want to do nowadays is to make this what is called robust. So if your aircraft may be operating with different fuel weights or at different flight conditions, you can produce a design which is overall very good, taking uncertainty into account. So where does high aspect ratio come in? Sorry, second equation. In fact, I've lied. There's a third equation. This is the one we want to worry about. So this is saying that my drag goes down if I can make that aspect ratio so the length of the wing's bigger. You're all familiar with contrails. That's an effect of the high pressure underneath going around the wingtip to the low pressure on top of the wing. The strength of these contrails is a function of the amount of drag there. So the longer we have the wing, the better we will be able to reduce the drag. So that's our advantages for having high aspect ratio wings, so longer wings. The disadvantages are that possibly we need to have extra weight to make it there. We tend, if we don't have lots of extra weight, that the wing becomes more flexible. And does this high flexibility reduce the gains? One of the other important things is the size of the airport gates. So 737s and A320s are limited by a gate size that is 38 meters. And if the plane were that little bit longer in its wingspan, the airlines will be charged a lot more money. So it's one of the things driving this. And also we can't use conventional designs for this as well. See the trend? So this is, again, looking at the aspect ratio. So the aspect ratio is roughly a function of length divided by the chord, the width of the wing. And we can see how over the years we've trended along, and things like 787, 777 have aspect ratios of 10.5, 11. So we're not dealing with enormous great aspect ratios. What problems do we get in modelling them? When our wings start to bend up a great deal, we find that the force acts inwards, so that's called a follower force effect. And our conventional analysis methods, so industry would use an FE program called Nastran, for instance, that will give you the wrong answers. So if we're doing an analysis on a wing where there's a lot of deflection, we need to use specialist analysis, which doesn't exist in industry. We're not just interested in deflections, we're also interested in the gust response. So that's an aspect ratio of 10. So we get hit by the gust and it bounces around a bit. This is what happens on a gust on a wing of, say, 26. So that's very extreme. So comparing those two plots, you can see we're getting much more motion of the wings. Having motion of the wings is actually very good. I'm not sure the passengers are very happy. I admit to nothing to people I sit next to on aeroplanes when I start looking at the motion of the wings and things, because I have found that it tends to frighten them. But we need to have accurate methods to predict these responses. We talked about flutter, so we saw that wing vibrated a lot and then broke. If we're in this non-linear world, we can get something which is called a limit cycle oscillation, which means that we get motion, but it's limited. So, and you saw there that top one, the response got so far, but we don't get structural failure. But if we can't predict, if we haven't got the mathematical models that predict that, we then can't actually go and make a design. And the important thing is that that's not due to the flow stalling on the wing, that's just a function of these very large deflections. So, a couple of years ago we were involved in a study with Airbus, looking at the effect of increasing the size of the wing, doing a proper aircraft sizing and looking at dynamic and static effects. Remember, I was saying that current aircraft are designed to have an aspect ratio of about 9, 10, 11. If we just did a linear analysis, we get an optimal value of about 17, and that goes up to about 19 if we put a non-linear analysis in there. So the take-home message from that is that longer wings really do give you better performance, even taking into account all the things like flutter and gusts and stress. But to do a really good job, you need to do a proper non-linear analysis. So it's one thing having mathematical models. We need to go and do some tests to validate this. So this is a project called, AWE, and this is our high aspect ratio wing. And so we designed the wing and then manufactured it, which was essentially a big beam down the middle. So this is 2.4 meters long, and then various aerodynamic surfaces attached to the wing, and lots and lots of measurements as well, which we can use to validate our models. So that's the beam just after it was manufactured, and cut out foam in order to give us our aerodynamic surfaces, and then we end up with this model in the wind tunnel at Airbus. So as I say, that's 2.4 meters. This is about 3 times bigger than any other wing of this very flexible sort that has ever been tested. I talk about sensors, so we have accelerometers, we have aerodynamic tappings, we have strain gauges, we also have the 3D camera system, and all of that. So we have ended up with 38 terabytes of data, which we're still analyzing and seeing how does the test agree with what our predictions actually were. So this is showing the deflection along the wing. So that's at the wingtip, that's about halfway along, and this is using 20 meters per second, and this is at 2 degrees root incidence, 4, 6, all the way up. You see that when we get to 14, it drops down again, and that's when we start to get some stall, so we lose some lift. That was a photo taken at the deflection. So if that distance there is just over a quarter of the semi-span, so over 60 centimeters deflection. The 787 is perhaps the largest deflection at the minute, and that's only about half of that. So we're really sort of pushing into the unknown of being able to analyze those deflections. That's some of the twists that we got. So it actually doesn't twist. So the black line is showing what is the root. So we twist the root of the wing. So this is all on a turntable that can twist. So the black line is the black line is showing what that root twist is, and so then the elastic twist at the tip is the distance beyond there. So we don't tend to get more than 2 degrees twist all the way through up to 50 meters per second. And of course, not everything works as you want. We talked about separation. the wing is slowly increasing its angle of attack, and then on about the second week, this happened. Okay, so, and now the tunnel is being turned off, the turntable is being turned back, the time traces showed us that that oscillation was getting bigger, and then eventually everything comes under control. We were able to predict that in the end, and that was due to the wing twisting so much. So we got plus or minus 30 degrees, which is quite extreme. You wouldn't want that, obviously, to happen in flight. But from this, we can validate our mathematical models. Okay, so that's talking about some experiments to try to understand what is happening. The second part, with about the next 10 minutes, I'm going to be talking about how can we use folding wingtips. So we know that we want the wings to be longer because that gives us less drag. We also said that the gate restrictions stop us doing that. And so the idea is, can we use folding wingtips to meet the gate sizes? And then the question we started off looking at about 6 years ago is, can we get loads reduction from that? So this is the idea. You can go and buy a 77X today. Nobody's actually bought one of these options yet, where the plane will land and then the pilot will make the wingtips fold up, a bit like on an aircraft carrier. And so it's going to be able to fit into the airport gates, but it's also going to have the longer wingtips in flight. I think those are all artistic interpretations. I haven't got an actual copy of the photo of the real system. How does this work? How do we actually get loads alleviation? And the way we do that is by taking our fold, but instead of having it in the direction of the flow, we twist that. So here we're twisting by some angle gamma. And then when the wingtip moves upwards, we actually get a downwards deflection in terms of angle of the wingtip. So that's what we're trying to exploit. Okay, and this is how you would envisage it being used in flight. You would say that, okay, in normal flight, we just have this long aspect ratio wing, so it's very good from a drag viewpoint. If we start hitting maneuvers or gusts, we enable the wing to be able to float, and that reduces the load. And then when we land at the airports, we can then fold the wings up. Sounds futuristic. Certainly this folding wingtips is going to happen very, very soon. So what does that look like? So we've got our wing and we've got our tail surfaces there, but now the wingtips are floating, so they're held up by the aerodynamic forces, and then we go through a gust. So we click that, this is what's going to happen to the aircraft. So the wings go up, and then you can see that with the response to the gusts, we're able to go through the gusts and we can reduce the load. We don't believe that, of course, so we need to do experiments. So this was our initial prototype. So again, that's our wing with the cuts. Okay, forget about the gap. So what we got here is a wind tunnel, open section. That's our blue wing. And what we've got here is a very rudimentary gust generator. So this is allowed to make the flow change. And what we can see is that when we start moving the wingtip, so it goes up, the wingtip goes up, it moves down, the wingtip moves with it. And then when I start putting a gust in, you see we get that motion going up. So what we were doing was measuring the load at the root, and this is a slight, and we get a reduction. This is a slightly more improved model where you're sort of flying along. Again, we've got a hinge like so, and we've been doing a lot of experiments recently, again looking at the loads reduction and the best way of implementing this. So this is looking at the wingtip, so it's all 3D printed. So we have this folding hinge line. We can either lock it or leave it floating. In this floating section, we can actually then use a tab, and then we're measuring acceleration and strains on the inboard sections. So that's the wing. You can hopefully make out two what are called gust vanes. So these are like wings across the section, and we can move those up and down to mimic the effect of turbulence in the tunnel. And what this again shows, that if I apply the 1 minus cosine, so they go up now, and that is the motion. And by comparing what happens if the hinge is fixed or the hinge is locked, is floating, we can see the improvement. So again, they go, and that's the hinge. Now, whether the passenger is going to like the idea of your wingtip bouncing up and down 20 degrees, I don't know. I think by those days, we'll have planes without windows, and everything will just be projected there, so perhaps we won't see that. I don't know, but as I say, it works very well. Here's another couple of videos. The one on the left is fixed. The one on the right is the same approach, same condition, but with the floating hinge. Let's run that again. So why is that not going? So again, we get hit by the gust, and bang, and up it goes. So again, all the calculations are agreeing with our predictions. By having this wingtip hinge, we can reduce the loads. And remember, less loads is less stress, which equals less weight, which equals better performance. And that's what we're aiming for. Right. Okay, and the final thing we got to, again, working with Airbus, is something called the Albatross 1. And this is the first time that there was actually a flying demonstration of this.
You got the mission planner working? Okay, going in 3, 2, 1, go.
So this first flight is with the fixed hinge, which then provided us to see what the difference were with the folding wingtips. So we've now got, this is now free. So you see as we start taking off, they'll move up. Start getting aerodynamic lift. So I mean the motion is now due to the, going for the maneuver or the sort of turbulence in the flight. So there we go, they're responding to the gusts. So that's a really good example of universities working in hand with industry. So we're able to do short, small prototype tests in our wind tunnels, able to do analysis, and then tying that in with the more rigorous environmental appreciation from industry. So what have we covered tonight? I've talked to you a bit about the Royal Aeronautical Society. I've talked about why we need to be developing more fuel-efficient aircraft. Silver bullet of batteries that are going to fly us across the Atlantic are not going to be with us for 20, 30 years. I've talked about high aspect ratio wings and shown how they reduce the drag, but also talked a lot about aeroelasticity and loads and how we need to be careful of flexibility, but also shown how we can enhance the flexibility, again, using modeling and using wind tunnel testing. And I've shown you in these last 10 minutes about folding wingtips and how they enable higher aspect ratio wings to get the better aerodynamics, but because they're folding, they let you fit in the gate sizes. They also enable you to reduce the drag, but also then particularly they enable you to reduce the gust loads, which then reduce the weights. So they've got the potential to substantially reduce the fuel burn. So the research for this is ongoing. Airbus have plans for some more sophisticated flight testing, and watch this space. I really do believe we are going to see certainly folding wings on the ground and hopefully using this sort of technology in flight. So with that, I'll say thank you very much for your attention. I hope I haven't scared you off with too many equations, or for those of you who aren't aero engineers, about some of the things that can go wrong with aeroplanes, and I'll happily take any questions. Thank you very much.